Okay, chapter 7, we are looking at table design. Um, so, obsession with detail can be a good thing. When you're running out the door, it's reassuring to know that keys will be hanging in the hook where you don't always leave them. Same is true for database design. Developers tend to follow different SQL style patterns when naming tables, columns, and other objects called identifiers. Some prefer to use camel case, berry smoothie. Uh, just explaining of those cases. Then you'll find some passionate supporters of each naming convention. Some preferences are tied to individual database applications or programming languages. So Microsoft recommends Pascal case for its SQL servers. Mixing styles of following none generally leads to a mess. So in an example, yeah, we were looking at one of these customer lines. So we tend to try and look for a consistent naming scheme, so that it makes it easier for everyone to read and use the code in the future. So if we're using quotes around identifiers to enable mixed case, standard ANSI SQL and many database-specific variants of SQL treat identifiers as case insensitive unless you provide a delimiter around them. So here we did a bit of an example. They're just showing us here. So if we do a mixed one, when you execute these statements in the order, first create table command creates a table called customers. Rather creating a second table called customers, the second statement will throw an error. Because you didn't use a quote identifier, it's picking up that there's obviously that there already. So pitfalls, outgoing identifiers, I don't think we need to look at that. Guidelines for naming, so we must use snake case, make names easy to understand and avoid abbreviations for table names in plurals, and watch the length. So when making copies of tables and use names that you'll be able to remember and will help you manage later. So controlling column values with constraints. So here we have a check, unique, and not null. Check evaluates whether the data falls within values we specify. Unique ensures the values in a column or group of columns are unique in each row in the table. Not null prevents null values in a column. Primary keys, natural versus surrogate. So in chapter 6 we did the primary key, a column or a collection of columns whose values uniquely identify each row in the table. Primary key is a constraint and imposes two rules on the columns that make up for the key. So each column in the key must have a unique value for each row, and no column in the key must have missing values. Pros and cons of key types. As with most SQL debates, there are arguments for using either type of primary key. Reasons cited for using natural keys often include the following. The data already exists in the table. You don't need to add a column to create a key. Because the natural key data has meaning, it can reduce the need to join table. Alternatively, advocates of surrogate keys highlight these points in favor because a surrogate key doesn't have any meaning in itself, and its values are independent of the data in the table. If your data changes later, you're not limited by the structure. And natural keys tend to consume more storage than the integers typically used for surrogate keys. Okay, so here we're going to do a create table natural key example. So we create the table, giving it a constraint, primary key, then first name and last name, and then we do a drop table natural key example, and we create a table with a key example again. So we first use the column constraint syntax to declare the license ID as the primary by using the constraint keyword, then followed by the name for the key, and then the keyword for this primary key. And next we delete the table from the database using the drop table command, and aim a primary key using the table constraint syntax. We declare the constraint after listing the final column with the column we want to use as the key in the parentheses. In the example, we end up with the same column for the primary keys as we did for the column constraint syntax. However, you must use the table constraint syntax when you want to create a primary key using more than one column. In this case, you would list the columns in parentheses separated by commas. So here we go insert into example, inserting a first name and last name with the values. And then it'll give you an error because you're trying to do the same. So creating a composite primary key, you want to create a natural key, but a single column in a table isn't sufficient for meeting primary key requirements. For uniqueness, we may be able to create a suitable key from a combination of columns, which is called a composite primary key. So here we create a table, natural key, composite example, student, school date, present, and constraint student key, primary key with the student ID and the school day. Let's see, do you have those there? Have any of those to run?
I've been running them, these last ones, and there's duplicates.
Yeah, that's what I'm trying to figure out.
So at least it did it the first time.
Yeah, I did it the first time, it's fine. There we know about the duplicates with the errors, and it'll tell you where it already exists, which we know because every time we run them it gives us that.
Oh, yeah, it says the error.
Yeah. So if we're going to creating an auto increment surrogate key, so yeah, we created a table with surrogate key example, order number, big serial, product name with a character of 50, the order date, and the constraint order key primary key, which the James has run that for us.
The order number increments. Yeah.
Yeah.
Which is what we want.
And then we insert into surrogate key example and product name and order date and the values of beach ball Polish, and we tell its date, the atomizer with the date and a flux capacitor with the date, and then we select from the surrogate key example.
I've done it.
Listing 7.5 clears the big serial data type for an order number column, and the set column is the primary key. So yeah, we're running select wildcard from surrogate key example to see how much the column fills in automatically, which we have there that James has done for us, which is those three that we had. Foreign keys. With the foreign key constraint, SQL very helpfully provides a way to ensure data in related tables doesn't end up unrelated or orphaned. Foreign key is one or more columns in a table that match the primary key of another table. In the foreign key, it imposes a constraint. Values entered must already exist in the primary key or other unique key of the table it's referencing. If not, the value is rejected. So yeah, we create a table with licenses, license ID, first name, last name, and the constraint license key, and the primary key is the license ID. Then we create a table of registrations, same thing, registration ID and date, references license ID, insert into licenses, a license ID, first name, last name, and then we give it some values to insert. We insert into registrations. We give it a registration ID, a date, and a license ID. Insert into registration ID, registration date, license ID, the values of those, and then that will be giving us those there.
And you can see I'll run these last few inserts. It should give us errors, yeah. So it's already done.
So that's fine, yeah. So it gives us the error. Now the resulting error is good because it shows the database is keeping the data clean, but also indicates a few practical implications. First, it affects the order we insert data. Cannot add data to a table that contains foreign key before the other table referenced by the key has the related records, or you'll get the error. In this example, we'd have to create a driver's license record before inserting the related registration record. Second, the reverse applies when we delete data to maintain referential integrity. The foreign key constraint prevents us from deleting a row from the licenses before removing any related rows in registrations, because doing so would leave an orphaned record. Automatically deleting related records with cascade. So to delete a row in licenses and have the action automatically delete any related rows in registrations, we can specify that behavior by adding on delete cascade when defining the foreign key constraint. When we create the registrations table, the keywords would go at the end of the definition of the license ID column. So here we do an example. We do the registration date, license ID, references is license with the license ID, and then on delete cascade. Constraint is the registration key, and the primary key is the registration ID and license ID. That you have there.
Yeah, at OX, it's all got
You just
these
gonna, because it's already done. Yeah, it's because it's done already. Yeah. So then deleting the row in the licenses should also delete the related rows in the registrations. Also, okay, so that's fine. The check constraint evaluates whether data added to a column meets the expected criteria. The check constraint is extremely valuable because it can prevent columns from getting loaded with nonsensical data.
Let's check it out here. Failing row contains. There you go. The constraint violates check constraint. Check role in list. And this one. Also, failing row contains for relation check constraint example violates check constraint. Check salary not 0. And that was 0. There we go. So it worked.
So as with the primary keys, we can implement a check constraint as a column constraint or a table constraint. So down in this next example, use a check constraint applied to 2 columns in a table we might use to track the user role and salary of employees, the organization. So here if we create the table, check constraint example, so user ID big 0, user role, salary integer. So here we say constraint user ID key, and then primary key is the user ID. Constraint check role in list, and then the check is the user's role in admin and staff. And then the constraint check salary not 0. Check salary is bigger than 0, so anyone that's not 0. You want to run that one for us?
Okay. It's not listed. You mean this constraint grad check?
This one here. That's.
Oh yes, sorry. 7.7.
7.7, yeah.
Oh, here we go. No, we just did that one.
Oh, did you do that one? Okay.
Yes,
fine.
yeah. So I was confused. So So it's the
The
unique
unique.
constraint.
Okay, so the unique constraint, we can also ensure that a column has a unique value in each row by using the unique constraint. Unique constraint has one important difference. In a primary key, no values can be null, but a unique constraint permits multiple null values in the column. So here we do a create table. Do you want to run this one for us? Big serial, contact ID, primary key, the first name, last name, the email, and the constraint is the email unique, and the unique ID or the unique item must be the email address.
Oh, so I have created it previously. You can see a
Yeah,
unique
so
constraint example. Let's try the inserting. It should tell us no constraint email unique. There you go. Duplicate key value. Let's do this one. Duplicate key. And another duplicate key value already exists. Duplicate key values here, as it says here. If we insert an email that already exists, the database will return an error.
okay,
Because we
so
used
that's all.
unique. So next is not null.
Yeah, so not null. We learned that null values are not allowed in primary key because primary keys need to uniquely identify each row in the table. But there will be other columns besides primary keys where you don't want to allow empty values. To require a value in a column, SQL provides the not null constraint, which simply prevents a column from accepting empty values. So there we created a table, which you've obviously done. Removing constraints or adding them later. So to remove a primary key, foreign key, or a unique constraint, you would write an alter table statement in that format, which you've got there. Alter table, table name, alter column, column name, drop not null. So here you should have all these there.
Okay, alter table query return success. Fully 7.10, so we dropped student ID. Then we can add constraint. Then alter column. And then alter column again. That all worked. We made the changes to the table. And so, yeah, so that worked.
Okay, cool. Happy days. Did you do this?
7-Eleven. What?
Yeah, 7-Eleven. Have you got 7-Eleven there?
New York addresses, I should.
Yeah.
Yeah, I've done it. So it has worked.
Download, create a new draw. So yeah, we create a New York addresses table and import the data. Okay, so here we created the table. New York addresses.
I think
Long
I
and
did it. Yeah. Let's just go check the next one. I mean, we should explain that, but then let's check if it's just working. Recording some control execution times.
Yeah, those. Yeah, so there we have the run. Okay. 712. We run these one at a time. Select queries with where clause, but with the keywords explain, analyze included at the beginning. Instead of showing the query results, these keywords tell the database to execute the query and display the statistics about the query process and how long it took to execute. Okay, so there you've done that. fine. So there's the stats, which is fine. Adding an index. So if you want to add an index, change the query search method and how fast it works. In 7.13 we ran this here.
Create index, this one.
Yeah, then that will pop out with
Already exists.
Yeah.
Okay, so it's done it before.
No, that's done it before, so that's fine. Yeah, this is basically just checking speeds and how fast it returns results in a nutshell. Considerations when using indexes. Indexes are valuable, but they're not always needed. In addition, they do enlarge the database and impose a maintenance cost on writing data. So a few tips. Consult the documentation for the database manager you're using to learn about the kinds of indexes available and which to use in the particular data types. PostgreSQL has 5 more index types in addition to B3, one called IST, particularly suited to the geometry data types. Okay. Consider adding indexes to any columns you'll use in table joins. Add indexes to columns that will frequently end up in the query where clause. Use explain, analyze to test performance under a variety of configurations to ensure configurations if you are unsure. Optimization is a process. So wrapping up, with the tools you've added to your toolbox in this chapter, you're ready to ensure that the database you build or inherit are best suited for your collection and exploration of data. Your queries will run faster, you exclude unwanted values, and your database objects will have consistent organization. It's a boon for you and for others who share your data. And that was that chapter. So this chapter concludes the first part of the book, which focused on giving you the essentials to dig into SQL databases. And that was the end of 7.
Great. Thanks, Don.